Well, if you ever use the GNOME desktop for any length of time or on any weak or underperforming laptop, you might have run into some performance issues, and believe me, I sure did, and that's actually why I switched to KDE in the first place. The main problem you will have noticed though is probably that animations were not smooth and there was a noticeable lag between them. So while the GNOME desktop has undergone many performance improvements during the past few years, the real root cause of the issue was solved just a few days ago with the introduction of triple buffering functionality in Motra. As usual though, let's take a step back first. What is triple buffering? So triple buffering is a common trick in the book of pretty much every OpenGL implementation. When triple buffering is used for graphics rendering rather than rendering the entire graphical pipeline on one buffer, 3 different buffers are allocated in RAM and used in parallel. These buffers are allocated as follows according to Intel's documentation. Number 1. The writer thread uses one buffer to store the pixels that will be part of the frame as input. Number 2. The reader process listens to the second buffer which reads the pixel the frame is made of from the memory. And number 3. The third buffer is used as a spare, which allows the input and output threads to swap their buffers asynchronously. The advantage of this approach is that the graphical output tends to be much smoother because the GPU can begin rendering the next frame without necessarily waiting on the 2 main front and back buffers to be done with a current transaction. The third, spare buffer, can be used to calculate a new frame early on. The real only drawback of this approach is that in some implementations it can cause some latency. This technique is already widely used in plenty of video games as it comes free with every modern OpenGL implementation. The only reason why GNOME didn't use it yet lies in some matter architectural quirks. So let us now move on and talk about what happened to GNOME itself. Remember how we talked about the problem with the slow and laggy animations earlier? Well, the entity that led the effort to find and resolve the root cause that caused the symptoms was none other than Canonical, the company behind the Ubuntu desktop. The Canonical contributing heavily to GNOME is nothing new, since the Unity desktop was abandoned in favor of GNOME starting from the release of Ubuntu 17.10. Canonical has become a very important contributor to the GNOME ecosystem, consistently contributing upstream in meaningful ways and working together with the GNOME team to bring Ubuntu users a Canonical branded GNOME experience with the Yaru theme in such a way that existing JDK applications that rely on Adwaita theme would not break under Yaru. Ubuntu 17.10 running GNOME. Particularly, Canonical's focus has been on improving the performance of the GNOME interface, so there is no surprise that the work on triple buffering was led by them. Collaboration wins at the end of the day, and when multiple distros standardize on the same set of desktop environments, good things come out of that. Just think of all the good that came to KDE Plasma after Valve decided to use it on the Steam Deck. While it's not exactly comparable, it is a similar story. So while it has been known for a while that the GNOME desktop suffered for some performance issues, the root of the issue was identified in a more rigorous test around 2020. The Ubuntu team was playing around with GNOME, trying to experiment with further eye candy when they found out that the more eye candy they added, the more shell would slow down. So what's puzzling is that the cause of the lag did not appear to be inadequate computational power on the machines where the lag happened. On the contrary, the hardware was perfectly capable, but the GPU was underused while the lag occurred. The root cause of the problem was identified to be in the way that Matter renders its frames. Rather than using triple buffering, it runs all of the rendering into a single threaded loop, which by design has a very limited throughput. It was apparent from there that this was the limitation to work around to help with the performance concerns. Initially, work on making the rendering event loop multi-threaded with a triple buffered architecture started with the X11 session and frame clock changes. That initial part of the work was the more manageable part since it came free relying on GLX and X11 protocol that bridged the gap between X11 itself and OpenGL graphical APIs, which is also triple buffered. The limitation with that implementation was, of course, the fact that it was, well, limited. GLX is an X11 specific extension, it is hence not portable to Wayland, and for tasks that require GLX, modern Wayland implementation use EGL, a different API instead. Besides, rather than being based on a client-server architecture like X11, Wayland is just a protocol implemented by compositors such as GNOME's Matter. Porting this fix over to Wayland would involve dealing with actual Matter code with no shortcuts. From late 2020 to early 2022, Canonical worked on implementing triple buffered rendering on the Wayland backend. A higher effort rework to Matter's architecture had to be done to achieve the same result, to make Matter able to cope with multiple frames in flight simultaneously. What this means is that fundamentally the compositor needs to constantly be one step ahead. Before the GPU is done carrying out the work on rendering the previous frame, the CPU has to be already working on the next one. This works well because the CPU and the GPU are separate entities, and in a standard non-GPU CPU architecture, all the GPU does is take orders from the CPU, which acts as the central orchestrator of the whole operation. At that point, the work had reached a point where it was stable enough that while Upstreaming GNOME had not accepted it yet, the result started to be shipped in Canonical's own Ubuntu Desktop 22.04 LTS. You should know that Ubuntu does not ship a copy of GNOME that exactly one-on-one the same as Upstream GNOME. They do some changes. Several downstream patches are applied to it by Canonical and Debian. What this means for those who are running Ubuntu is that you have been enjoying the fruit of its labor for the past 2 or 3 years, while by default this was not true for other GNOME desktops or distros. Sorry. At last, in 2025, here we are. The patch has been accepted by GNOME, and it has made into GNOME 48, where it will bring a fundamental performance improvement to all distributions. It needs to be specified that the extent of the performance improvement varies between various hardware configurations. However, it never makes things worse, and it's only a range between a slight and unnoticeable improvement. As usual, by the time GNOME merges a merge request, it managed to be mature enough that no regression are introduced by adding it. Those of you who are more keen on the competitive online games will have been asking themselves, okay, but will this not add or increase the input lag? The answer is, in short, no, not in this implementation. Differently from most triple buffering implementations that are found in games, this one sticks to double buffering in all cases, unless when the system is unable to deliver the expected performance, and then only then does the algorithm naturally transition to triple buffering. Trying to make this simpler, triple buffering is only ever used when it's truly needed, and this is a big part of the reason why this implementation does not regress and does not make things worse on existing hardware. If you have been happy with the standard behavior and your system always renders GNOME animations at your monitor frame rate, then you don't have to worry about it. Odds are the triple buffered rendering behavior will never or very seldom get triggered on your device. If that is not the case though, triple buffering will just come in a clutch whenever your system cannot keep up, just giving you a subjectively smoother experience, all things considered. So are we done? Well, according to Canonical, no, not really. Implementing triple buffering at the compositor level is great, a great milestone, but it is not quite the be-all end-all. Several applications still need to do some work themselves to enable triple buffering and reap the full benefits from it. As an example, Canonical notes that it seems like Firefox struggles to render the first few frames of the touchbar scrolling physics when flanked with a touchpad, unless the machine is set to performance mode. There is nothing in your Wayland compositor, there is nothing that your Wayland compositor can do about this issue. It is just Firefox domain, and they are expected to come up with a comparable solution to work around this limitation eventually, just like GNOME and Canonical did for Matter. So are there any limitations? While triple buffering seems to be overwhelmingly good, Yes, there are sadly some limitations to this approach. The main one is, well, you guessed it. Come on, you did. If your system is running an NVIDIA GPU, odds are you will be not reaping the full effects of this performance improvement. The reason is that the NVIDIA driver is, as always, very different from standardized Mesa implementations and only supports explicit sync, which is comparatively synchronous, whereas every other GPU driver also supports implicit sync, which is asynchronous. When implicit sync is supported, you can pass buffers around without waiting until the GPU is done rendering them, which can result in a healthy performance speedup and is essential for dispatch to work. Since NVIDIA does not support this, however, you will not be getting the same level of performance on these cards. You should probably read a Xaver article on explicit sync to know more. One rare limitation is that users who run Linux on a virtual machine with software rendering will only get some benefit from this implementation, but not nearly as much as non-NVIDIA physical GPUs will. Besides, Canonical recommends running desktop environments that do not rely on any graphical API like OpenGL at all on sessions without graphical acceleration whatsoever, since it's more expensive for the CPU to emulate a GPU with LLVM pipe that it is to run a non-accelerated graphical session anyway. And that was everything. That was very technical, but sometimes it's good to be technical.